Last week, we had the opportunity to run through an intro class, a recap, just asking ourselves, what is public health? Where do we fit in this whole arrangement? Today, we want to start off with the first topic, which is, on-site wastewater treatment. And we defined this last week. Just a moment, I want to get some photos here. Great, I have them. And right, so we ran through these slides just to get an understanding of what is, and so what we want to do in this lecture. We said that last time we did mention that I'm hoping that you can see my screen. I am on the first slide. And so we said that, yes, the course that we have covered until now, we are looking at the municipal conventional wastewater treatment. And but it's not, it's not every time that we have the opportunity to design a system or where all the units that are being served are all together as it would happen in an urban setting. Sometimes we have isolated development. Sometimes we have, the system does not exist at all. And in fact, of late, there has been a thinking of saying, look, there are places where people developed system 100 years ago, and every engineering system has a life. And so the systems are aging. So if you are to it is expensive to really to start thinking about, reinstating this system. It involves massive work, massive opening up of grounds. As people say, well, why don't we then develop decentralized systems beyond the fact that it is having isolated development? Would we consider developing decentralized as an approach to more sustainable wastewater management? These systems comes in many ways. And one of the ways it can be simple things that we know, like septic tanks. It has to do with individual systems or various. It can be clustered as here. It can be a package, more like a generator. Generator is a packaged power generation plant. It comes and it is sold as ready to install. So you can think of a generator as a packaged power generation plant. So in a similar way, you can think of how can I package. Yes, Susan? You have a question, Susan? You do please go to the chat area. Susan, confirm if you have any issue, yes or no? Okay, Susan has come and disappeared. Okay, all right, Susan. So I'm saying that consider the same way that you package a generator to generate power, you also can condense and package a wastewater treatment plant on it's ready to install. And then you have the other system that could be, for example, large capacity. Ordinarily, we have septic tanks that serve us for one residential unit, maybe two, maybe three. But also you can have a large capacity that serves 800 people. There, that system is there. The rule of the thumb is that the septic tanks, we do them for more than 400, 400 people and less, 400 persons and less. So that is to think, if you think about an average of about, 4 or 5 members, you're talking about septic tanks would ordinarily serve between 50 to 100 families, or maybe we say as one up to about 100 families. But it is possible also that you can use the same principles and do a large capacity septic tank. Now, what do we mean and what's the difference between conventional and on-site? And I think we see that well, it's conventional because we see that when public health was developed, it was developed from an urbanizing point from the municipal. And so the convention has been to collect all these waste together to a centralized point of treatment. That's why we call it a centralized treatment scheme. And this is really what you find as conventional across many places in the world. But when we talk about on-site, we mean that it is not connected to a centralized sewer system. Secondly, is that the wastewater, unlike the centralized system, where we transfer waste from the point of source to the point of treatment, in the case of decentralized or on-site wastewater treatment, the water is treated, very important, is treated near the point of production. At or near the point of production, very, very important in defining what decentralized wastewater treatment is, what on-site wastewater treatment is. It is a system by which the wastewater is treated at or near the point of production. And this almost always, but not strictly true, involves a primary settling system, or what we call a septic tank. We are going to discuss a little bit more in details how to design a septic tank, things to consider. But a septic tank, in the simplest way, is a primary settling tank. And so we hold water there for not more than 48 hours, preferably 24 hours. During that time, the readily settleable materials settle and the water goes to the next stage of treatment. Therefore, if you see somebody telling you or trying to design a septic tank to hold water for months, then that's a problem, because we only hold the solids, not the water. But and therefore, most on-site treatment system will include a septic tank as a primary settling tank. I think I did see this already, that the term decentralized is used interchangeably with the word on-site. And now, when we talk about on-site treatment system, one of the things is that we are talking about water. In this instance, and I'll come to that hierarchy, we are mostly thinking about water-based sanitation or waterborne sanitation, because you could have things like the pit latrines, which are on-site, but they are not water, they are hygiene methods. But as you're talking about water, waste water. So that means we are looking at systems that are where the fecal sludge is water transported, is waterborne. So we will not deal here with issues like latrine or what we call dry sanitation method. We are dealing here with waterborne sanitation methods. And so what are the reasons for utilizing on-site sanitation systems rather than centralized sewer systems? One of them is because of the cost. If you are to think of a town like Nairobi, you need billions of shillings to areas that are not connected. but therefore it provides us with developing on an incremental basis in terms of affordability, and we reduce the cost of transmission of wastewater. So one of them is an affordability issue, that it is cheaper to do a decentralized system as compared to wastewater. I mean, to a centralized sewer. Of course, there are the pro and the cons, because the treatment system now comes in as a cost. The second thing is the fact that sometimes we want to rehabilitate older systems, but no, instead of refurbishing everything, you just tackle that area where it has deteriorated, and you provide a decentralized system there. And the other thing is also to avoid what you call the early capital investment. You don't want to do a sewer system now going to Isinya, and yet you will not have a settlement in Isinya until the year 20 years from now, and therefore it allows you to invest as and when needed. So one of the things is, therefore, in a nutshell, it is the benefit of a cost benefit, and secondly is the issue of flexibility that allows investment to happen at the same time or in concordance with the demand for it. The other very good reason is about the opportunity to recycle. When we do recycle or reuse of water, it means that the water is treated near the demand for. You see, for example, if you think you're in Karen and you have delivered water to Dadora and you treat it to reuse level, how do you get that water back to Karen? It's an expensive system. But if the water is near your house, then you can treat it and reuse it. Because it is the wastewater does not require another transmission and pumping. Because if it was going by gravity from Nadora, means to take it back to Karen, you have to pump it. So it becomes more difficult to encourage or to operationalize reuse issues. The other thing, I talked about the flexibility. I talked about the cost because of the distances or whatever. And then the other important thing is when you have isolated development, in which case then connecting to a centralized sewer becomes a huge problem. You can think, for example, if you have, what can I think about now? Think if you are in a town like Thika, and there is a development somewhere, 40 kilometers, and it's a small town there coming up with about 200 people or 400 people, then it doesn't make sense to do 20 kilometers to where the sewer is. It becomes very expensive, and therefore it becomes good when you have isolated development. So, on this slide, we are looking at the various methods of on-site treatment, and looking at asking ourselves, remember something we said, why are we doing this? And I would ask you, Susan Pamboy, why are we doing this? Why are we developing on-site systems, sanitation systems? Why? Pamboy and Zawadi can also assist. Go to the chat area and tell us why. What is the reason really why we are doing this system? What is the objective? Remember last time we talked about problem-based approach. Problem-based approach. There is an objective why we are doing this. You travel to a place for a holiday. You travel to a destination because you are attending business. You travel to a destination because you're going to do research. So the issue not whether you fly, whether you use a bus or use your own vehicle or you cycle. It is why are you making this journey? The reason you're making the journey then influences how you do. And you'll be saying, well, if I am going for a meeting that is tomorrow and the distance is 400 kilometers away, then cycling is not an option. So there are certain things I'll be asking. So in this journey, I think about the time, about how much I need to transport with me, affordability, things like that. So in this case, I can see a number of people are typing. Why really are we supporting or are we engaging in on-site wastewater treatment systems? I'm waiting. Right, to serve remote areas. What is in this service, Mr. Wanyoni? What is in this service? What is this service about? Right, so I see Zawadi to reduce contaminant level, correct? And so we want to reduce the contaminants, right? So therefore, reduce the disease transmission, correct? So here again, about preventive measures. So all those things, Humphrey, Benta, and I think also Zawadi. So we are reducing the contaminants and reducing the exposure to disease risks and contamination. Very important, Lorna, that we are preserving human dignity. Of course, that's why otherwise we just do a toilet with a flush without the walls. But we also create the walls to give dignity. That's why we go and we do male and female toilets, because we want to preserve the dignity of the user. Very, 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 very important. So we have health risks, and the second is the dignity. Why else? Why else? It collects and disperses. This is about this. I hear you, Frank, but you see, this is a process. Collect, treat, disperse. Why? Why are we collecting? Why are we treating? Why are we dispersing? We are doing that so that we can reduce the disease risk, or what you call the public health risk. And so we are treating the water, the wastewater. Now, several people are typing, and which is fine. Please, 1 minute if you can finish your comments. Has solved the water scarcity problem. Banis, I see you. I see what you say. Products of Gabriel, right? So that comes back to the groundwater. So there's an element of a recovery of material or energy, either by reinjecting the water as a material, reinjecting it, or reusing it. Now, you may use the word of frankly, we want to collect, treat, and disperse. The first question becomes, what are we collecting? If you look at the table that we have up the screen, we are collecting the fecal sludge and the grey water, and the water that we use. When we think about the waste that we produce in the house, we have fecal sludge and we have the water that we use around there. We see that if we do the water supply, it comes out, we use it either for flushing or for other domestic uses. So there is either the grey water or the black water. So this system must be able to must collect fecal sludge and also the grey water. The second thing is ask then, how do we treat it? And by the way, as we treat it then, so we say it should be able then to treat both the fecal sludge, manage the fecal sludge, and also the wastewater. What it has collected, it also must go to treat and then disperse it safely. Why are we doing that? So the first thing that you're saying, it's a capacity to collect the waste. Secondly, is that it must be able to treat it safely to reduce public risk. And the third one is that we remember we do it in a dignified manner. We are giving people dignity. So when you look at open defecation, does open defecation give us an opportunity to collect the sludge? No. Does it accept grey water? No. What is the human dignity? Very low. What's the public health risk? Very high. And therefore, open defecation, and it will be surprise you. Has anybody come across incidences of open defecation in our country? Has anybody come across this? Yes, I'm trying to get sorry, nimetangatanga pahali. Yes, in rural areas, in slums, yes. Let me just try. I'm trying to share my screen. I want to share this window. Just a moment. Let me see if I can share this window so that I can tell you how serious or how not so serious this issue is. Just give me 1 minute. Let me get this up the screen. Okay, let me see now if it will come. Pick it. Yes. Now, can you see that image? I hope you can see the. Yes, I see you, Wesley. So, can you see that image? Yes. There's just certain two maps of Kenya, right? Two maps of Kenya, right? Now, so when you look at that image that we have up there, what you see is that the map on the left, you see that very many of our counties, for example, the whole of Wajir, Turkana, more than 75% of the population, we have 75% of the people defecate openly in the field. When you look at Marsabit, Pokot, Mandera, Tana River, and what have you, more than 50%. When you go to Isiolo, Garissa, Kitui, Kilifi, Kajiado, Narok, Homa Bay, I think Wesley mentioned about Homa Bay, Migori, Baringo, all these areas, we have 25% and 50%. Now, only very few areas, very small percentage, perhaps 25% of the country, luckily, is the same area which has 80% of the population, where we have sanitation improvement of at least 25%. And they, you're saying that people at least with a latrine, eh? That's, we talk about improved. People that at least are a latrine. So what am I trying to demonstrate with this? What I'm trying to demonstrate with this is just how serious the problem of open defecation is in our country. And it's therefore is something for us as engineers, we need to think very, very seriously that it is indeed a very serious problem. I'm back now to the slides. So we're seeing a lot of our people are having very undignified ways of just doing very basic human things. I mean, that's then what are we engineers for? Of course, we have things like then where people then, they don't defecate, but then they throw it away from where they live, especially in the slums. Again, very low dignity, very high risk. And remember what? When somebody goes and defecates openly somewhere, whatever it is, that waste eventually finds its way to the river because there will be water. If not in the river, there will be dust. And that dust, when you go to your desk today in this country and you leave it for 2 days and touch it, it is full of dust. That dust is so if somebody urinated somewhere in the open, that translates to dust and it gets to you. It gets to the things that you hold and touch. If somebody then, of, what do you call this thing, throwing sputum, ovio, everywhere, that eventually does go to the air. So the fact that I have a good facility for, washroom, for my sanitation, does not create immunity in the manner in which we are exposed to health challenges due to poor health conditions elsewhere. When somebody washes with dirty water and throws it and drives the water or disposes the water off the street, You have wiped my shoes and everything else, and I just dispose that water on the street. Or there is a leaking or overflowing sewer, and it goes to the street or to common areas. Eventually, this has a way, one way or the other, to finding itself to interact with the way we live, or otherwise to the river, and therefore complicates our treatment. So remember, that's why we say it's a public health. They affect large scale of the population. And so the issue of environmental health, and someone mentioned it, I think that was Elvin Langat, that dealing with ensuring environmental health, environmental cleanliness does affect is as important as the manner in which I engage the treatment, or all the other public issues. When you take contaminated food, when people make food in an unsanitized or rather in an unclean environment, when, for example, the factory setting, and so there is contamination of sugar or flour and what have you, with oil, with grease, with mercury, with all those other contaminants, eventually they come to. So public health, it's something, you're not doing it for others, you are doing it for yourself. You are doing it for every one of us because it concerns all of us. That's just how important. Of course, for us, we are only dealing with the waterborne hygiene issues, the waterborne, but there are other realms of public health concern. Any question up that far? If there's any question, please put it up the screen. Kuna swali? Okay, if there's none, then I continue. So we are saying, of course, then we have the bucket. Some places, I think, Wajir, we are still using the bucket system. Many of our prisons, they're still using the bucket system. And yes, they can do fecal sludge, can't handle grey water. Of course, low in human dignity. Um, Now, I'm back and apologize that we have having a bit of a problem with my regular connection. So I'm trying to connect this through the phone hotspot. So in case it fluctuates, you'll understand. I really am sorry about that. But I hope that then you can hear me. Confirm? Thanks. So we were saying that then, as we go down the list, then our hope is in the decentralized is to go really to the last two, where then we have high level of on ability to manage the fecal sludge. We have a capacity to accept all the water, both gray and black, that is generated within the households. We sustain high level of human dignity and also, low risk to public health. What am I also trying to say here is that the decentralized systems on-site systems are not low technology. They are only isolated or off sewers or off centralized sewer systems, but they require high level of expertise and they have a capacity to solve huge problems. In fact, you can think, imagine today you are the engineer or the chief officer for water and sanitation in Wajir County. How would it be? What is that you can do to quickly accelerate the rate of hygiene or the improvement in sanitation? If you are today in Baringo, where you're having 50% of the people, what is it we can do to ensure that children in school, people setting up restaurants, government offices, private offices, they have a capacity and even, they have access to improved, modern, dignified. Because this is a charge that we have as we leave school and we go out to the various places where we will exercise knowledge and competence. And further to say that we really are what are our duties we see to solve the challenges facing our country and the humanity at large wherever we work. So now, what is the problem we face in sanitation? Of course, very many of us have had have interacted. Some of us grew up, some of us maybe see it in newspaper, but we have seen a pit latrine. And let me exemplify this problem. And we want to exemplify this problem by thinking of somebody who takes a shower in a basin. Is that a shower or a bath? That's a bath, not a shower. In a basin. And use 20 liters of water. But let's say this person owns 100 acres of land. And he showers 2 times in a day or bathes 2 times in a day. So as they take their shower, he, pours out the water in his 100 acres. Believe you me, if that's just one person, you will not see the effect because as soon as he pours the water, it is taken up by the soil. What if there are 10 people and they shower 2 times in a day, in the various places, they are spread out in the 100 acres. Again, you will not see it. Maybe even if there are 100, you won't. But if there are 10,000 people who take a shower 2 times in a day, using 20 liters of water each in 100 acres, and each of them pours the water out, then you will start finding that you can actually, it's just becoming mucky. The ground is always wet. You start getting the smell. You start sensing contamination. You can think of the same if it's a person who lives in that 100 acres and eats a banana every day, just one banana. And as they take their walk around their farm, they throw a banana peel. By the fourth day, the first banana had dried. So if you come after 10 days, you're not going to see 10 banana peels. You probably will, if you're lucky, you might see 2 if you're lucky, because it is within such a huge expanse of area. If there are 20 people, probably you may see 5 that are still fresh, but nothing really to cause you alarm. But if you have 20,000 people living in that 100 acres, and each of them takes, so you're talking about 20,000 peels of banana thrown around every single day, then you start, it's a nuisance. By the time you get 1 month, the place is rotten and smelly. So what am I trying to do with this? I am saying that on-site sanitation is not a problem when you have a few people or low density and sufficient land area. But it is a big problem when you have dense population or high number of people living in a small area, because the disposal start becoming a challenge. The likelihood that the contamination will or people come to contact with contaminated effect becomes more and more likely. So what I have there is to say that sanitation is a big problem. It's a big problem when you have a population, a big population, and that's why in the low-income areas, these are huge area. And generally speaking, in a area with more than 800 people per hectare, we see that's a densely populated area, and so on and so forth. Now, just to say that, yes, sanitation problems are there everywhere, but they become more intense in areas that are heavily populated. Now, I have already said, yes, this is Humphrey saying, did we start by saying that it might be cheaper to do on-site sanitation than connecting to centralized sewer? Why then are we saying that it would be easier? It will be easier if money is not an issue. Okay, I won't get that clear. Probably, I think what I've been saying is, maybe I talked about money in, maybe I'm dreaming about it. But I think what I was saying is that it is easier when we have land. No, not at all, Humphrey. We are saying that it is easier when we have land. And what is the, look, when you do municipal, I'm trying to reply to Humphrey, when you do municipal sanitation or wastewater engineering, you'll find that the transmission, or let me say this, any system we have, and I like the word that I think someone used, which said it is collect, treat, and disperse. So whether it is centralized or decentralized, and the collection system is the same. You have a cistern, you have wash hand basins, so the system within the house remains the same. The cost of the collection remains the same, whether you are using a decentralized system or centralized system. The second thing is then the treatment. In the case of decentralized, you are using facility within your area, a septic tank, and maybe other improved aerated systems. You could have that. In the case of centralized system, you don't have treatment immediately. The treatment is common in a central place. But what is the difference? The difference is now comparing and saying between this treatment system here and the one that is in that is centralized, what is the per capita cost of treatment? But what makes the real difference is the transmission, that sometimes you have to transmit that water over 50 kilometers, over 30 kilometers, over 10 kilometers to a centralized place. That transmission cost is not there for on-site wastewater treatment because you're treating it at or near the point of of treatment. Oftentimes, that works out better. But that's a nutshell. Secondly, is the operations issue. If I am then beyond the capital construction, there is the operational cost. Then we start employing this huge amount or number of people who have to ensure that you deal with the blockage, you deal with the leaks and everything else that goes with it. So beyond the capital investment, there is also the operational cost. So in the end of it, you find that the decentralized system often, it is not, there's never 100%, but oftentimes happen to be cheaper. It's the benefit is even added when you consider that you have an opportunity to reuse water or wastewater by utilizing decentralized system. And I like what Mugoni has said there, that yes, of course, that the cost viability need to be analyzed on a case by case, but oftentimes, rule of the thumb, decentralized systems end up being cheaper. So I have already explained by this, going back to the slides now, that why is this an important issue to us? Because we are seeing that, remember, we talked about improved sanitation, and we said in some counties, good number of them, Lamu, Muranga, Nakuru, Kericho, we have improved sanitation, meaning at least there is a pit latrine. But right now, only about 21% of the homes in Kenya or the population in Kenya use a waterborne sanitation. So if we are going to grow a modern society that we aspire to be by 2030 or so, then we have a huge job to ask these other people. By the way, the 85 includes somebody who's using a septic tank. So this is waterborne. So you may find only 10%, I don't have the statistics, but you find only about 10% are connected to centralized sewer. Some places, even in Nairobi, like Karen, Syokimau, those kind of places, we are still using, you're still using septic tank. I'm sure even in Juja, outside the university, there is many people who are still using septic tanks. So a majority of the people do not have connection to centralized sewer. Secondly, that we are having rapid expansion of technology and of people and development. And therefore, it means that the suburban areas are growing very high without centralized sewer. We need to serve them. And then this centralized sewer, because of limited professional input, we have very high failure rate. When you go outside Juja, outside the university, and you look at the number of septic tanks and a lot of areas where the wastewater is flowing on the surface, it is a sign of, actually it's a failure in the system. And therefore all this then becomes a major threat to environmental health. And that's why we are discussing these issues. Now, and therefore a basic conventional system includes a pit latrine, a septic tank, and a disposal trench. We'll be designing each of these, looking at especially this, how to design a septic tank and how to design an effective wastewater dispersal. So there is the source, there is the treatment system, the primary treatment, and the secondary treatment. Remember something we said. We said that these settles readily settleable solids, and these provides treatment for dissolved organics or BOD and others. The good thing with also disposal in this manner to the soil is that you also have an opportunity to take out a nutrient using plants. So that's a conventional on-site wastewater disposal. Of course, there are always, as always, this is a typical, there are other variants that can be added. We'll discuss cases where you can add oxygen in this chamber. We will discuss here where you, other than using soil, what other methods can we use to hasten infiltration and so on and so forth. Let me take your question, Mogaka. You've seen that I've noticed a situation, I've noticed in Mombasa, is that residentials cannot connect to septic tank to pipelines that end in the ocean to get rid of the overflowing grain. The rock callers have not followed up on that. I would like to get your opinion on that practice. Interesting. Not only in Mombasa, in fact, you look at the most of the old towns, they actually used to have a pipeline that used to the septic tanks that used to take their water to the ocean. You know, and not only that, if you look also at very many schools and government done in the 60s, 70s and before, you find that it used to take the wastewater to the river. Because by that time, remember dilution is an acceptable method of dispersal. If I have only one person living by River Tana, truly, even if that person wastes their whatever their daily waste there, it is so insignificant that really doesn't cause anybody any problem. The same case I said is a problem of the area and density. But now, that is when the population was the way it was. Now things have changed. The consciousness about the care, environmental stewardship has also increased. You know, we never used to talk much about environmental stewardship before 1992. 1992 years. We never used to talk much about it. UNEP was only formed in 1982 when people started getting more conscious about environmental degradation. So yes, Mugaka, this is something that need to be arrested because as you're seeing, when too many of these facilities then dispose to the ocean, then as you said, the incidence, the magnitude of the problem becomes very high. All right. Let me go to the next one. And so the major components then is a septic tank, is a soil dispersal, and therefore is a soil rather, and the absorption field. Three important things. How do we design a septic tank? What type of soils do we have? And can they accept our waste? And then the dispersal field. How do we design it? And so let's start thinking about the first part of it, the septic tank. And the septic tank can be either one or two chambers, okay? One or two chambers. And then it allows water to come in here. It allows water to come out and then to go to the soil. A few things you'll notice very deliberately. Let me keep, I'm trying to get something to write. If you look at this water level there, you'll notice that these outlet pipes, this outlet arrangement regulates the level of the water. And you'll notice that the inlet is slightly about 150 millimeter above the level. Why do we do that? We do that to prevent backflow. Okay? Very important. Otherwise it will clog. It will induit this system. So you see that the difference between the inlet and the outlet, there is a certain level to ensure that this is not flooded. Number two, there is something that we call the inlet-outlet arrangement. You see here, as you go out, as you come in, you will notice this place. Let me pick another color. I hope I have that color. I don't know I have. No, I'm not getting that. But you notice that this one comes up to that point. Okay? So this goes into the water about approximately 200 millimeters below the surface. And it has two reasons. First of all, is as water comes in here, it has a bit of speed. It has a bit of velocity, it has a bit of energy. Velocity gives water energy. So this means that the velocity is dissipated by draining or introducing the water into the chamber, and therefore does not disturb the rest of the system. The second important thing about that is that imagine if that outlet was somewhere here. Imagine if it was something like that. What does it mean? Sorry, I'm not doing a very good one. It means that over here, oops. Sorry, no. This thing is becoming very complicated. It's doing things I didn't tell it to do. Yeah. So it means that here, there are gases that form in this region. These gases will go up the pipe. And where does the pipe come from? The pipe has come from your toilet. So it means that the gases go back to inside the house. Maybe a few of us have experienced that at one time when you flush the toilet, you get this pungent smell, this repugnant smell. Because why? Let me see if I can get that. Maybe just to. I hope I'm not being too slow. Let me see if I can demonstrate that to you. Okay, let me just try and get this and explain to you something I want to do. Let me get this. Let me share my screen. Window. This. Okay, I hope you can see my window. Can you? There's a picture there, an image there of a toilet. Confirm you can see it? Good. Thank you. Now, who would tell me why do we have that water? You see this water here? I don't know where water is. Oh. You see this around here? You can see this water and you see it in the toilet. Why do we have it? Who would tell me why we have it? Gabriel. Correct, Gabriel. Now, you see, and let me use the next image. So you see that this is a toilet and this is a system leading to the disposal. So yes, now you see this image. I hope you can see now the image that is in blue. And what do you see here? You see that this is a place coming to from the toilet, and this goes out to the outlet. So if gases come, if we have gases, I'm trying to look for a pen. And I hope you can see the gases accumulate around the outlet, the outlet area. Now, where is this thing now? Around this area on the left. So what happens is that when you flush, remember this gas has been accumulating, and so there's a pressure buildup. So when you flush, these gases, as the water goes to the septic tank or out, these gases rush towards the toilet. And therefore, that's when you whatever. So this seal, this water trap, this water seal is very, very, very important in a water system. And therefore, to avoid these gases from coming there, and now I go back to my earlier slide. Now I'm back to the screen. We actually ensure that this is buried inside the water so the gases, or at least we minimize. Of course, you know that you also have the vent, just where the toilet is. Inside when you're doing the construction of a house, we provide a vent pipe so that instead of those gases accumulating just next to the seal, we get them to go in the air. It's simply a functional thing. Now, so in a similar way, you see that the outlet arrangement is also in the water. Why? Because when you open a septic tank, you will see a layer of solids, or what you call scum, accumulated here. If this arrangement was not there, then the scum would come right through, okay? It will come right through there and then clog the soils here, because these are solids that, all this area you have floating solids there. And so if then this is not provided there, then you'll find that these solids would go right through. If this T arrangement is not there, this will go right through and come to the soil and clog the soil. So after some little period of time, you find that your system then does not take in water because it has clogged the pores in the soil. So that's that's the first important area, the inlet-outlet arrangement. Secondly, the septic tank is a reactor. Now, who will tell me what's a reactor? Alex Mugo, what's a reactor? What do you understand with a reactor? Alex? And also Abdi Malik Muhammad, what do you understand? Where compounds are broken. Yes. Check for me. Abdi Malik, what do you understand? And Daniel Mithamo, you can also help us. Alex? Mithamo, are you with us? Daniel? I'm waiting. And anyone else for that? What do you understand by a reactor? Come on, someone. What's a reactor? Surely. We all can tell what a reactor is. Good. So someone says it's an apparatus or structure in which fissile material can be made to undergo a controlled self-nuclear reaction. Zoka, Mary. It is where material microorganisms break down the compound into less harmful, right? They are where chemical reactions occur. It's a closed space that encourages chemical reaction. Aerobic biochemical processes occur. All wonderful things. But I want to pick a few things. Please don't stop. You can go on. I just put yours as well. Don't worry. But I want to encourage you a few things that I'm seeing. One, reaction. See, some people are saying biochemical, others are saying chemical, others are saying nuclear. But a reactor, a reaction takes place. It's a place where the reaction takes place. So in a septic tank, is there a reaction taking place? Yes, because we are converting biological matters to less harmful system. So there is some reaction that's undergoing. Two, I wonder what I'm seeing. Some people have said, I think I see it with Mary about controlled. So it's a controlled environment. So therefore, second is that there's a controlled environment where reaction or process takes place. The other one that we have seen is that there's something produced, be it energy, be it your growing material, and so on. So there is a consequence. And so two most important things, it is a controlled environment for certain processes, certain reactive processes. And in our case, what we are having is biodegradation. And so being controlled, it means that there can be no water going out or coming in during that process. Because we talk about what do you call it, retention time or detention time. So if then water, when you design this tank, you design it for a particular period to hold water for an average of the particular detention time. So if water goes in or out, other than to the designated points, then you cannot assure that. Secondly, if then these gases and everything they produce is whatever is the products are not contained, then they go out anyhow. And therefore, all these things we are saying, how do we manage the gas, how do we manage the solids, how do we manage the water, then doesn't. So it's a controlled environment. So therefore, that reason, the septic tank must be watertight. So the material and the technology used must ensure there is no water coming in or going out. None of them is good. The other thing that's the second thing. The third thing is that we have an inspection chamber. Very important, that the only thing where you can be able to see what is going in there is through the inspection chamber, or what you call the manhole. Very important. Another very important thing is something we call the plug flow conditions. The ratio, the length to width ratio. Now let me try, I'll just use here. Imagine that's the shape of my septic tank in plan. Okay. And so let me say this is 1 and this is 1 meter there. And so I have water coming in there and water coming out there. Now, what do you think this water will do? Is that water approximately spreads in 45 degrees. Okay? So the water comes in there and spread like that. But then by the time it gets here, this is the outlet point. So the water needs to go out. So it starts converging towards the outlet. Now, that is your effective area. We call these areas here, this one here, we call them dead corners. Meaning that the water there is no reason for water to come from here and spread out this way. It will not spread that way. So it moves this way and moves that way. Water doesn't move like that. It moves in the path of least resistance. So effectively, as you can see, half of your plan, of your tank sub-plan area is not effective. Okay? The second thing this does is that think about the same also in the depth configuration. Now when you go depth-wise, and you have this one here, and you have that one there. So the water will not come down all the way up to here. It will actually go like that. By the time it's getting there, it starts going up. Is that true? So what again does it mean? That again, another half, only half. Now, only a half of your tank, 50%. So only 50%, so in terms of the plan, 50% is lost. And in terms of the depth, 50% is lost. That means effectively only 25% of your designed volume is actually effective. So if you had designed this for a 2 days detention period, it actually does it in 12 hours because of the configuration. So there are certain things then that we do to change that scenario. And one of the changes that we do is to make this longer. Make that longer, so that then there is a longer period for travel before it starts converging. Okay? Sorry, this thing is misbehaving. Before it starts converging. So it means that the ratio of the dead corners to the entire tank is very small. And the ideal is 3:1. That the ratio of the length is, or width to length, is that the length is 3 times the width. Okay? Is 3 times the width. So L to W is 3 times. So we call that plug flow conditions. This is where you are using gravity. If we are using a mechanical mixer, then we can use, in fact, it is ideal to use a box, to use a cuboid. But when you're using gravity flow or hydraulic flow, then it is ideal that we use a ratio of 3:1. I don't know, that's number 4. And therefore, how do we solve for the other one that we talked about? Let me get this out. How do we solve for the other one? For the depth part. The depth part, we do it by that, sorry, let me get the right color that can be seen. So we do it by, so you have that. And remember we say that these will tend to go down this way. So of course the length helps, but also it means that we don't make this very deep. Because if you make this very deep, it means that then this takes very long to get to there. Okay, so we limit the depth. In fact, the depth of a septic tank is limited to 1.8 meters. 1.8 meters is the length, is the limit we give. So, and again, you also don't want to make it too close to the surface, because it means as the water flows, it will keep on disturbing the settled matter. Okay, because some matter like what you have seen here settles. So if then this gets very close to if this, for example, builds up somewhere here, it means it will keep on recirculating the settled matter. So the depth is between 1 to 1.8, 1.2 to 1.5 being more rule of the thumb. And of course, the material here that we are using for the wall need to be non-corrosive. And finally is that we provide space for the storage of solids. Now, um, so that's something about. So remember we had said that we have three important systems: the septic tank. Let's go to the next one. And of course, I think I've discussed all these issues, so no need to go there again. And this one we will work on it. But very important, let me mention that approximately 30% of the BOD is deposited in the septic tank. And this one I'll leave it about. Now we come to the second system, which is the soil absorption. That the soil is a treatment media. When you use a septic tank, actually you don't treat the wastewater in the septic tank. Please write that with a red pen. You only retain the readily settlable solids. And that's part of the reasons that contribute to the 30% reduction in BOD. But by the time the water is leaving the BOD, it is still carrying 70% BOD. So if you had a BOD of 250, you still are carrying forward approximately 175 BOD milligram per liter. The safe disposal requires you to bring this to below 30, preferably even below 10 milligrams. So the water is still very rich in organic, dissolved organics. That treatment, the soil, in case of a non-site system, is both a treatment and also a dispersal media. Okay? Uh, Humphrey, where is 1.8 meters measured from? From the surface of the water, not from the cover, from the surface of the water. How many, why do some septic tanks have compartments? What's the engineering purpose? A very good question, Humphreys. Let me come back here and explain. Look, you see here, you have sludge. What happens as the sludge comes? You find something like this happening. The sludge accumulated like this. And as more of this happens, what happens still is that then you find this spreading out. If this one was not there, then you find this one spreading out. And as more and more of this happens, then you start finding that. Now look at this outlet and compare it to the level of the sludge. What happens? The likelihood that the sludge will actually get out onto the outlet becomes very, very likely. So this compartment here keeps this sludge from actually coming to the outlet area. And therefore, what then you would, even if this septic tank was apologize again for this. And so I think what I was saying is that then when you have this, what happens is that then the accumulation is around there. So in case there is this fills up entering, and before the this is dealt with, then this doesn't come. There's also a risk that some could come here, but then you see it provides a bit of safety. So long and short is that this then, and what you'll find with many septic tanks, you'll find something like this. They are shaped something like that. That's what you'll find. So that then this area, in fact, we normally provide this area as approximately 25% because of the storage of sludge. So when we have calculated the volume for powers of hydraulics, we add 75%, 25% to provide for sludge storage. And so I hope I've answered you, Humphreys. Now, I did mention already that BOD is removed at that level. And we were talking about the soil as being both the treatment and also the dispersal media. And we'll come to that, but then we see that the septic tank, again, very important, remember, is not a maintenance-free facility. It's not a maintenance-free facility. It needs to be dislodged between 2 and 5 years is really extreme. In fact, for me, I say every 2 to 3 years, it needs to be dislodged. Why do we do so? I want to refer you and I want you to read what is it? I want you to read something a little bit about the settling theory. And if you remember, or segmentation mechanisms. Let me see if I can get this somewhere. The settling phenomena, okay? And I just want to jog your memory or types of settling, okay? The types of settling. Let me see if I can get this image up the screen. So, if I share this screen, what pick it to? Share screen window. Yes, I reckon you can see what I have there. Now, there are types of settling. Okay, and from the types of settling, you remember we did something about glycerin and the cylindrical ball. I want you to read about this discrete settling. And the second time is what we call the flocculent settling. The third one is what we call the hindered settling or zone settling. I hope we are all together. Confirm, Charity, that you can hear me. Okay, and the last one is what we call the compression settling. Each of these has an implication. Suffice to say for now that the compression settling is about squeezing the water out. Like we do in a building. We say when we do a structure, there it settles by compression, by driving out the water between the soil particles, or what we call consolidation. Now, consolidation, in case now of organic matter, remember, this is matter that is undergoing reaction. And as it undergoes reaction, it produces heat. And when you have a reaction, there is heat, then there is transformation of the substance. Unlike soil, which is inorganic, and therefore does not undergo any reaction to the water that's pushed out. This one pushes the water out, there is reaction, a different, the product is different from the original. And so this hardens and it becomes impossible to actually dislodge it, because it's just as we are doing about the metamorphic rocks. They start becoming such, it becomes a continuum substance that you cannot dislodge through the normal mechanical systems. Therefore, when we have these solids settled for a long time, you start losing the volume of your reactor. So it is very important, that is long and short, that the tanks are dislodged every 2 to 3 years. If you must really extend for whatever reason, never more than 5 years, but on average between 2 and 3 years. And I encourage you to read through the types of settling, and that will be one of your questions in the assignment. I'll send another one. Of course, then we have said that there's some of the typical things that we have talked about, and so I don't want to deal with them. I go to the absorption fields and say that this is a system by which you distribute the water to the soil through a system of pipes and other technologies that are available. But I want us to go to this here, the trench, and you see how the trench is, this demonstrates. So you can see that this is the ground. This one here, there is a pipe, and it is surrounded by gravel. So it means that this gravel allows free flow of water from the pipe to disperse to the ground, and therefore protects it from clogging by soil. You can see that there is this distance here. The distance is sufficient to ensure that there is no physical damage, but also not too deep. In fact, this whole depth is about 0.6 meters, at the very, very most 0.9 meters. And that means, why do we do that? Because we also want the nutrients in this soil to be taken up by the plants. Okay. So, and we know that the root zone normally goes approximately 200 millimeters below the ground level. And therefore, by ensuring that this is not too far down, it means the nutrients and the water can actually be taken up and also dispersed to the atmosphere through the plant action. If this one was too deep, goes to a 1.5, then you have this one here, then there are very few plants that actually can get their roots beyond 300 millimeter. So purposely, rule of the thumb, your trench is approximately 0.6 to 0.9 meters deep. Right. The other thing then is that then we come to the soil. And when you come to the soil again, of course, this is the most ideal soil, clay, what you call the red coffee soil, clay soils, and, not the expansive type. When you get something like this, you are very happy, because these soils, they have a capacity. You can see what you're talking about, the plant. You can see the roots, where the roots are. That's why we are keeping the trench around that area. Okay. So that then the roots of the plant can actually, so you have there, you surround with the gravel, and therefore the roots can come to this area and therefore take the nutrients. Now, and of course, this means that also as they take the nutrients, then the water can keep on dispersing down. The water can keep on dispersing. And when you have this kind of deep soil, then you are very happy. Remember, there are two things happening, or about two mechanisms. First of all is the is the, and by the way, what we also do, also these roots do, they send oxygen to this area. And you know that organics plus oxygen, then we are able to degrade. So the degradation of the oxygen of the organics takes place, and the water is dispersed. And as the water goes through, this is a filtration, it's a mechanical straining. You know, it's just like if you were to pass water through sand, it filters out. So the bacteria, the solids, and everything else. So as the water goes deep down here, then we see that we are able to also filter. So by the time water gets, if the ground table is somewhere there, then by the time water gets here 5 meters, 10 meters, 20 meters, it is clean and does not contaminate the ground table. So what is the risk that we might face? The risk would be, what if the groundwater was here, where you have high level of groundwater? Then you have a problem, because it means then this starts contaminating groundwater. What if this is impermeable? Okay, what if this is impermeable rock? Then tuko na shida ingine pia. Okay, hiyo shida inakuja hapo. We have that problem as well. What if that is impermeable rock? So therefore, the soils need to be right. For what if the soils here have very poor transmissivity, that if you put 1 liter here, it takes a day to go? Then the quality of the soil where we are disposing this also becomes extremely important. And so this is just a normal configuration, and a few things to say, that the distance between the various trenches is about 2.5. The maximum length from end to over our trench is about 30 meters. And the reason for that is that, you know, if you know, these are distribution. If you think of it, you're having a trench there, and you're having a pipe coming down this way, and then releasing the water through perforations. Okay, if you take this to be the pipe, okay, you take that to be the pipe, and this is a trench. So as you go down here, there's a very high likelihood that by the time the water gets here to 25 meters, 20 meters, all of it has been taken out, you know, so that this place remains permanently dry. So to encourage distribution, you limit this to about 30 meters, okay? So, and their methods, remember, we had their various methods of distributing. One of them could be these trenches, what you call absorption field, and also the most common one, which we call the soak pit. It's the same thing. It means that we come here, and then instead of all this arrangement, okay, you just have a soak pit there. Just have a pit there, okay? And so this water comes in, and you fill this with gravel. But now remember what we have said. There are certain benefits we lose. Yes, it will disperse this down, but then we lose the nutrient removal benefit. And you know, also the plants, as they take the water, they also release the water to the environment through evapotranspiration. So all those technologies of disposal systems are available. Please also take a look, and I think that will be the second question in your assignment about the soil dispersal systems. I want you to look at that, and I'll send you the question accordingly. I can see now it's going to 1 o'clock. I'm still very far, but let me see how quickly I can run. If you were to do the dispersal by trenches along a steep area, the trenches runs along the contours. If this is a slope direction, this runs along the contours, okay? I have discussed this already. And this heap here is very, very important, because what it does, it keeps the water away, because we also don't want to get this trench, and so surface runoff ends up here. So we do that molding on purpose to keep the water away from the trench, so drive the storm water away. That's why you have that molding. Hiyo ingine tumeongea, but also very important here, you see that we have that facility there, which is a membrane. And the purpose of the membrane is it stops the finer particles from clogging this area so that you can still maintain free flow of water. That is the purpose of that. Okay, so what are the things that affect the successful siting of an on-onset water treatment? Of course, there is a proper site evaluation, is the design of the system, is the proper installation, and operational maintenance. And what are the common causes of failure? Is unsuitable soils. We have discussed that. Shallow rock, restrictive horizons, very fast or very slow percolations. If it is very fast, it means then it goes down very quickly without filtration and without proper treatment. And we have said that the soil is both a treatment and a dispersal media. And also high water tables. We've discussed all that. The other thing is about overloading. You see the water has a capacity of what it can take safely. If it is much more, inaweza kuitapika. It is start overflowing. We have seen that too often. The issue of the solid migration to the drainage field, we have talked about that. Remember, we talked about the buffer, and I'll show some photos here as I conclude, is the issue of the buffer failure. Remember, when you talk about the outlet arrangement, we see that the outlet arrangement stops the migration of solids to the drain field. So if there's a failure there, then we see the migration of solids. Now, these are very interesting, and you can also search on your net what do you call the root infiltration in sewer lines. Remember, the sewer lines are rich. Whereas we came here and said, look, this allows the roots here, okay, to come close, okay? Then some of these roots find their way to this pipe here because the pipe is rich with nutrients. And so it clogs the system. So that, this is what is being demonstrated here. So it finds through the joints or through a crack and gets in. And therefore it forms, because that place is rich, it is good. The issue of the traffic damage, and I think you know the various ways of protecting, sewer lines, whether concrete or plastic, wherever you have traffic, and the very, very common just user behavior about disposal of solids, about the disposal of solids. So, and I'll show some photos, and you know that the kind of things that we put sometimes in the toilet, then that does not help us to sustain the use and good use for that matter. So I'm seeing your question, Wangai. When the septic tank is dislodged, where is the excess sludge disposed? Wangai, you remember when we spoke last time, we looked at the cycle, we said, good, we supply water, we are very happy, but unfortunately we get wastewater. We get wastewater, we are very happy that the water has met the standards, but then we are left with the sludge. Now, what do we do with the sludge? That's our topic number 3. The treatment of sludge and sludge liquor. So, yes, we'll come to that. When you get this sludge and you dislodge, what do you do with it? Because we said it's still not safe. Therefore, that's our topic number 3 in this course. I hope I answer you, Wangai. So then, and so the overloading is something else. The overloading, and there are 2 types of overloading: hydraulic and mass loading. Because you can have a septic tank or a disposal field where you have little water, but has a lot of BOD, 3,000 milligrams per liter. The soil has a capacity. We call the self not purification, but the self is called what's called is a carrying capacity. It has a capacity of, just like you, the way you have so much, how many biscuits you can eat, or how much wine you can take, or how much water you can take. The fact that water is good doesn't mean that you can take 5 gallons of water in a single day. You can't. You have a sin beyond that, start becoming harmful. So soils also have the same carrying capacity in terms of water, hydraulic, and also in terms of the constituent solids, mass loading. And so overloading for either then can cause a failure of the stuff. And I think these are the factors, very important factors, and I think we'll read them in the notes. Soil, wastewater characteristic, is the water hot, cold? Is it heavy with, has it got other things beyond organics? The user lifestyle, temperature, operational maintenance, rainfall, and surrounding development. I'm looking for a place to stop now. Let me see which slide. I think I will not. How much time do we have, Harriet? Up to 1:30? Harriet, confirm to me on this chat. 1:30. Okay, let's do up to 1:30. Let me see if I can run through quickly. And what affects the soil? We have talked about it: the texture, the structure, the depth, the compaction, and the landscaping. The slope and all that. And of course, the same soil that you use for irrigation, the same soil classification that you use for irrigation, depending on this, then you can check the permeability and what have you. Okay, the same table that you use when you're doing a soil classification for irrigation also applies to this. And we'll do an example at some stage to show that. I've talked about overloading, and we are saying that we do this is that this is, and you'll see how we apply this, which is a typical figure that is used in Western countries. And when you look at some of the formulas, you'll see how it applies here, and therefore how can we adjust it for our purposes in case our per capita water consumption, not wastewater, about this per capita water consumption, if it is different. Some countries, North America, Australia, they have a much higher consumption. In some countries, including some part of our country, maybe again we have a lower, even up to about 15 liters per person, depending on various things that you by now know very well. Therefore, it's just warn you that when you look, for example, like the British standard, they actually you are using, or they use this per capita consumption, and as a basis for design, because they have their data there. And as I was saying, once you look at the soil type, then you can look at what I call the loading rate, this hydraulic loading rate, and therefore there are figures, and these figures are available from empirical evidence. So what are the things that can, we remember what we are looking here is things, we said things that affect the performance. This is what we are looking at. Factors that are that affect the performance. And we have seen the soil, talked about the loading rates. We are now going to the characteristics, okay, of the user. There are people who have a habit of showering 4 times in a day. Some shower once in 2 days. Some take, they have a toilet that can flush with 2 liters. Others use 4 liters to flush. People who wash and they keep the water. So all this, what is some people who dispose garbage, those that don't. Some people use oil. What is the time in the residence? Are you there for 4 hours in a day? Are you there for for 24 hours in a day? So all these need to be factored in when you are designing your on-site wastewater treatment. So long and short, as I said, it is not a lot of, it requires a lot of good professional input to work well. So the other thing is the characteristics of the water. And generally speaking, we saw that any water that has more than 250 milligram BOD, we say that water tends to be a bit, and maybe between 250 and 350 is medium. 150 and below is low strength water. When the water starts getting above 250, 350 especially, then that is a high strength water. It means that the risk of overloading by mass is very high. When you come to the example, we will see this. Whether the water, what are the constituents? For example, if you're doing biological treatment, which we do in a septic tank, and then you're using bleaches like G and others, and antibiotics, what does it mean? It controls the growth of the microorganism in the septic tank. So that the characteristic of wastewater affects how effective your system is. And that from the constant point of view, but also about the volume. So do we have, this is a typical, hourly flow rate. So are you having a more uniform? Are you having some that with a very high peak? And then after that you have, so depending on the characterization of flow and strength, then that affects your work. And of course, we're looking here at typical, concentration of the various wastewater, just for you to reference. Then, of course, we have said also that the wastewater, you're also looking at what is it wastewater that just has got pathogens? Because if it was just for washing gallons in a dairy factory, then it will not have a lot of pathogens, but it may be rich in other nutrients or so. Therefore, so what are the pollutants of concern that are there? If I'm doing tannery, then I know here I have to deal with chromium, for example, which I know has a problem with the environment. Maintenance, I think we talked about this, that yes, this system is not maintenance free. They need to be dislodged every 3 years or so. The temperature, of course, low temperatures means that the biological life is not as active. The plant life in the disposal field is not as active, or it's not as thriving. So we are seeing that 50% loss for every 10% drop in temperature. Luckily for us, we're in a very good environment here in Kenya, but your degree does not mean that you only work in Kenya. You can find yourself in South Africa, you can find yourself in Ukraine, or even in Canada. So then you find a different circumstance. Daniel, please put your question on the wall. I'll answer you as soon as I see it there. And I'm hoping that everyone is hearing me. And therefore, if you have rainfall, then it adds to the burden of hydraulic loading. Okay. And the question then is, who regulates these systems? One of the bigger problems we have is that whereas the civil engineers will do systems like septic tank, the regulation is under public health office in the county governments. So unfortunately, they are not. So there's a problem there. Engineers haven't taken too much interest. Therefore, we find that it's treated more like a hygiene issue. And therefore, a lot of things that we are discussing here, then they don't get as good attention. And I think for me is to urge you to take a bit more interest in your research work, in your reading. Take a bit more time. There's a lot of material relating to this area, and I think it's an area for now and for the future. Okay, and because it's not regulated, then you find that we don't have very clear performance targets. So what should a septic tank? What would judge whether a septic tank is good or not? Only when people see it. Only realize when it is full. What is the normal schedule of maintenance? What is how much the public know about it? Where can you have a septic tank and where can you not? Who goes around to ensure that the septic tank is actually maintained as it should? What about then the uptake? How are we renewing or what can we do when you talk about now IT and ICT? What are we doing to make the septic tank actually modern? How are we utilizing? We are seeing the IT or ICT technologies in every area. Are we also seeing this also going to the septic tank and or basically on-site wastewater treatment system as as we would think it would. And so the reverse then means is what is needed. So whatever is a problem, then we need to think about have routines for O&M, appropriate application of technology, certified practitioners, more education to the users, and so on and so forth. And so these are references which you may want to listen to look at, and there are many others. Just go to the web, look for septic tanks, look for on-site wastewater treatment system, look for decentralized system. There are numerous videos, there are beautiful text you can read. Please get in there. I think in the next class we'll be asking ourselves something, because we have dealt quite a lot about septic tanks. How can we make the septic tank work better for us, especially when we have constraints, as we have said, like constraints in terms of land area or constraints in terms of the soil disposal conditions. So the next topic is advanced on-site wastewater systems. But before we go that, then let me show you a few photos that you may understand why this is a good thing to keep thinking about. I think it's very good myself. So now this is a septic tank in one of the leading hotels out of in the town, a very, very, very big brand. And now, so you can see that if you look at this is the first chamber. So when you open it, first and foremost, if you ever come to a septic tank and open and you find that there is no bubbling, we said one thing about the reactor, it produces material or energy. And septic tank is anaerobic system. Because we are not injecting oxygen, it is anaerobic. But whether it was aerobic or anaerobic, there will be gases being produced. In case of a septic tank, because it is anaerobic, we have methane gas, among others. Now, so when you see a septic that is silent like this, and the solid mass is intact and quiet, then you know there's a problem immediately, because it tells you certain reactions are not happening. Now, that is one. So before I invest, but then you can see some of the things here. You can see Colgate and a lot of papers, that many papers and what have you. The disposal of solids. This is a top-notch hotel, so it just exemplifies the kind of thing we have in many places. Sorry, I'm trying to get the minis to play, and I don't know why they're not playing. Now, you can see here, you can see a bit of water there, although you can see it, but a lot of, now what was causing this is that they were using some chemical, some detergents, washing chemical. When this chemical, when it comes with hot water that is used for laundry, then it would form some woolly something. Okay, that's what you're seeing here. So again, the characteristic of the water being treated becomes important. This thing is frustrating me because now I have to keep on stopping to share and all that. And I'm trying to play the slides, but the slides are not behaving well. But I'm just about to, I don't know how this, let me see. Let me see what I can do. Okay, I think I just have to make do with. So now, okay, actually, let me just share the screen. I think other than sharing the window, let me share the screen. I think it might be easier that way. I share the screen. Okay, and so if you see this then, so you can see what happened here. That because of that mass, you can see this mass around here. I don't know that you can see it. There's a mass around here